right. Hello, Rebecca. I hope you had a good weekend, and I'm happy to be back this week talking to you about temperature and standard states and other chemistry things. This is the last part of the very first section of the book and of the curriculum, which is exciting. Congratulations, you did it. So we'll move on to 1.2 next. So we'll get into some new content, I guess tomorrow that'll be. But today I want to finish up talking about temperature, and then we'll do a little bit of review. And you'll have an assignment that's kind of based around that, and I'll give you some resources to review and practice these things, as you'll want to do that as we look forward to the IB exam, which is far away, but still we want to always be thinking and preparing for that. So here's a bit of practice from what we were learning last week. I want you to sketch and annotate a heating curve showing both the melting and the boiling of a substance. So you could pick anything you want. You don't necessarily need to label the temperatures or the times. I just want to make sure that you know what a heating curve looks like and how to label the things. So take a second, draw one of these in your notebook, see if you can sketch the correct curve. Okay, so I looked at these last time, right? They look something like this. This would be like for water because we've labeled 0 and 100. Just got to remember these plateaus, right? These would be when it's transitioning. So this would be like the solid state of water, and then it is melting here, and then we get the liquid state of water, and then it is boiling, and then gas, right? So your curve should look something like that. And also it's important that this is longer than this, right? Because it takes more energy for the liquid to completely escape the interparticle, intermolecular bonds than it does to just simply weaken them here. Oh yeah, I put all this stuff on there. Okay. Solid, melting, liquid, boiling, gas, right? So today, I want you to think about this. Why do so many temperature scales exist? Take a second. Think about that question. Why do we have so many different temperature scales? For instance, in the United States, we use Fahrenheit, right? Pretty much everywhere else, Celsius is used, right? Kelvin is what we will talk about a lot in chemistry, and these are actually very closely related. But we have all of these other temperature scales as well. You can see some of these conversions down here. So take a second, maybe pause the video, think about why do we have all of these different scales? Why do they exist like this? I'll give you a second. Okay, so unfortunately, I wish we could have a discussion about it. It's much more interesting, but I'll talk about some reasons why I think they exist and how some of them came to be. But yeah, so first of all, let's start with Kelvin. Kelvin is the scale that we're going to use in chemistry a lot. It is really useful because of that absolute 0 point, right? Which is the point where there's no more molecular motion, right? So this scale was created for a specific reason. It's an absolute scale. We have a 0 point, even if it's only theoretical. It's really helpful when we start doing calculations around temperature. Celsius was originally created based on water, and water's freezing point, which is 0, and its boiling point, which is 100. So it's really useful in everyday life. That's why it's used in most places. Fahrenheit was also created in a lab for various reasons. I forget exactly what it was based on, but Yeah, the difference of 180 degrees Fahrenheit between the freezing and boiling point of water um, is highly divisible and is mathematically useful, right? Um, so each of these scales was created based on different things and different measurements, like Celsius is based on water. Some of these are based on other substances that make them useful in certain situations. Um, but in chemistry, we're going to use, well, both of these a lot. But Kelvin is like our absolute scale, so it's useful. But this kind of highlights that science evolves based on context and practical application. But then as we get into this globalized age where people are communicating over these vast distances, we need a standardized process. So that's where like Kelvin comes in. If we can relate back to a standard like Kelvin, then we can make conversions between all of these different temperature scales. So let's look at this. Here's some questions. What are the temperature scales being used on each thermometer? Right, that is the first question. How do we convert from degrees Celsius to degrees Kelvin? It's the second question. And then the third question is, what is the change in temperature between the freezing and boiling point of water in degrees Celsius and degrees Kelvin? So look at these three thermometers, right? They're labeled K, degrees C, and degrees F, and see if you can answer these questions. Maybe pause the video, I'll give you a second. So, as we look at these three thermometers, we can see some different data points, right? So, for instance, we have mercury boiling at 630 Kelvin, which is 357 Celsius or 674 Fahrenheit. The steam point or the boiling point of water, right? We can see we're used to this Celsius, 100 degrees Celsius, that is 373 degrees Kelvin or 212 degrees Fahrenheit. We have approximate room temperatures here. Kelvin, it's kind of nice, 300. And then we have the ice point or the freezing point of water, right? 0 degrees Celsius. This is where nitrogen boils. So if you know what liquid nitrogen is, this is the temperature at which it changes from a liquid to a gas. Liquid nitrogen is super cold, and it is therefore useful for a lot of things. And then absolute zero, right? For Kelvin, that's 0. Celsius, it's negative 273. And for Fahrenheit, it's negative 460. So I kind of answer that. This is Kelvin, right? This is Celsius. This is Fahrenheit. If we look at degrees Celsius and degrees Kelvin, we can notice something, right? Kelvin starts at 0, and then at the ice point, at the where ice becomes water, right? We have 273 degrees. Celsius is negative 273 degrees at absolute 0, and then 0 at this melting point, right? So 1 degree Kelvin is equivalent to 1 degree Celsius, but they start at different places. The way that we convert, it's really simple. You just add 273, and this actually isn't super accurate. It's 273.15. So if you have a Kelvin temperature, if you have a Celsius temperature and you want it in Kelvin, you just add 273.15. That will give you the amount in Kelvin. You can do that for any of these temperatures. They just don't have the 0.15. So what is the change in temperature between the freezing and boiling point of water in degrees Celsius and degrees Kelvin? We can see that in degrees Kelvin it is 100, and that is true for Celsius as well. So 1 degree Celsius is equivalent to 1 degree Kelvin. It's the same amount of heat energy, right? Fahrenheit is different, right? It does not correspond 1-to-1 with these. It is a different scale. So that conversion is a little bit more convoluted. Yeah, so here's the conversion, right? Converting between degrees Celsius and Kelvin. You will want to know this. There will definitely, be questions about this on the test. Just remember this number, right? 273.15. This is also, I can't remember if this is in the data booklet or not. Yes, it is. And so I haven't given it to you yet because I haven't been there, but you're going to get a data booklet with a bunch of measurements and things, including this value. And that data booklet will help you. You'll be able to use it on the test that I give you, and you'll also get it on the IB test. So this is actually in that. So you don't necessarily need to remember this exactly. You just need to be able to find it in the data booklet. And I'll see if I can get someone to print that off for you